Welcome back, everybody. In this video we're going to perform object detection and tracking via the speeded up robust features or SURF functions in Emgu CV. In this video we're going to use Emgu CV and VisualBasic.NET in Visual Studio 2010 Express Edition. However, if you prefer a different environment for OpenCV or Emgu CV development, the code we're going to go over today should port pretty well to any other OpenCV or Emgu CV environment. This video is going to presume the knowledge of the previous videos. Please view the previous OpenCV and Emgu CV tutorial videos if you have not already. Let's get started. Okay, so let's get started today by taking a look at the program we'll have when we're done. And here it is. And so we're going to have the choice of performing surf detection on still images or on a webcam feed. So let's start out with some still images. These first two are the images that ship with OpenCV and Emgu CV. So we have this box here in the garbage with some other boxes next to it. And you can see the surf detection algorithm finds it very nicely, and the way we have our program set up, we can either draw these matching lines in green and then also the key points, or not draw either at our option. And let's take a look at some other videos. Here's a stop sign on a corner, and then a drawing of an ideal stop sign. Why don't I make this a little bigger so we can see it all? And there we are. We can see the stop signs found very nicely. And here we have the Sauber BMW F1 car and the Intel symbol. Now in these images, I should mention at first when I was going to do this video, I was actually cropping out what was trying to be found and then using that as the image to find, but I kind of decided that was a little bit too easy. That was cheating. So in each of these images, the image to find is either a separate image at least, if not a ideal image drawn separately in a word processor. So there we are. We can see we get a nice detect on the car there. And let's go ahead and take a look at some webcam footage next. So here for our first object with the webcam, I have this stamp book, Statue of Liberty Forever. Let me see if I can get it to auto zoom a little bit better. Let me turn out this light here. There we go. And if we hold it like that, so it fills the camera up a little bit better. And again, I have to kind of manipulate it a little bit to get the auto zoom to work. And then we press Get Image to Track. Try and get the whole thing on the screen there. Bear with me for just a moment. Apparently I'm not that good at holding things up to cameras. There we go. And let's go ahead and turn off the autofocus at this point. It'll work better without it, and now we can pan back. So what we're going to find when we use live webcam footage here is that you kind of have to move the image around a little bit slowly. If you move it quick, it'll lose track of it. But as long as you don't move it too quick, we'll get some pretty nice live tracking there. It's good, and we can turn off the lines if we feel they're kind of obstructing the image a little bit, or we can even turn off the key points too and just look at the red box. So again, you see there, as I'm moving it, sometimes it loses it for a moment, but it sort of retracts it. And the surf algorithm is rotation invariant, so we can turn the algorithm, the image rather, this way. It's still going to track it just fine. Here we can see the key points twist all around. But as long as we keep the image nice and square to the picture, it shouldn't be affected. And you can see it's relatively distance insensitive until we get too far away, and then it can't recognize it. So next, let's take a look at on the other side of the stamp book. Here we have the individual stamps, and we have some flag stamps and also some Statue of Liberty stamps. Let me turn the autofocus back on so you can see it a little better. There you go. And just so it fits the camera a little bit better, I'm going to tilt it 90 degrees. We have the resolution set to 640 by 480. And bear with me for just a moment here. Again, my coordination apparently holding things up to cameras isn't that great. And just another moment here. There we go, that's pretty good. And again, we'll turn the autofocus back off. It seems to track better that way at a distance. And we can see this doesn't track quite as well as the other image. It doesn't have quite as many distinctive key points, but it tracks pretty well. And there we go. Let's go ahead and turn on the matching lines. We get pretty good tracking there. And this one section, the lighting isn't quite so good in my apartment here, but the other three sides of three corners rather of the image, it tracks pretty well. And again, it's rotation invariant, so we can rotate it any way we'd like. As long as we don't move it too quickly, we are going to find it's going to track pretty well. So there's that, and just as one final object, I happen to have a tape measure handy here. So let's go ahead and use that. And this isn't going to track quite as well because it doesn't have quite as many distinctive key points as the stamp book did, but it'll track reasonably well, we'll find. And there we go, that's pretty good. And let's turn on our key points and matching lines again. And our autofocus back off. And we can see it tracks pretty well. Not quite as well as the stamp book, but once we kind of slow down a little bit, give it a chance to get caught up, it'll find it. And there we are in the corner there. And once again, rotation invariant, so we can turn it any which way we prefer, as long as we give the computer just a moment to catch up and perform its processing, it'll find it. And let's go ahead and take a look at a few more still images here. Here's this Beverly Hills sign in this scene here, and then here's the image to match up to. And again, these are different images. The image on the right is not cropped out of the one in the scene. You can see the shade of the sign is slightly different in color, and it finds it nicely. And then we also have the Beverly Hills sign in this downtown city scene. And once again, it tracks pretty nicely. And again, we can turn off the matching lines and the key points if we like and just look at the found object. And finally, let's end on this crossing sign here, railroad crossing. And there we go. So that's the program we'll have when we're done today. So let's take first a quick look at some of the theory and background of the surf algorithm, and then we'll go ahead and fire up Visual Basic and write our program. So we're going to find, if we do an internet search on surf detection, the first, or well, in this case second page that pops up is the Wikipedia page for the algorithm. So this opening paragraph here gives a nice summary. Please refer to that if you're interested in some of the background on the surf algorithm. And here's a table of various implementations of the algorithm. Of course, the one that we're most interested in here is OpenCV Surf, beginning with OpenCV 2.0. And of course, we're using Emgu CV as a wrapper for OpenCV today. And then at the bottom in this external links section, you're going to find the website for Surf, and this is a website by the authors who actually came up with this algorithm. And here there's two papers on it, this one from 2006 and then this one from 2008. Let's go ahead and take a look at the one from 2008. This is really a very well written document. Definitely, if you're interested in the details of how this algorithm actually works, give this a read. It's only 14 pages, and it's really very straightforward and easy to follow. The algorithm's kind of complicated, but this paper does a really great job of explaining it. It has a lot of nice, some formulas, but it's not overly math heavy. There's a lot of nice images and, kind of diagrams and things that explain how it all works. And of course, this is written by the authors themselves, so this is really the authoritative document on how this the surf algorithm works internally. However, in keeping consistent with the prior videos on my channel here, rather than going into theory any deeper, I'll leave this for you to read later at your convenience. And for now, let's go ahead and fire up Visual Basic and have at it. Alrighty, so we have Visual Basic started up here. Let's go ahead and start a new project, Windows Forms application, and we'll call it Surf. And choose OK. And then we'll start out adding our references as consistent with the previous video. So we're going to go to Browse, and then C, Emgu, Windows x86, bin, and these 1, 2, 3, 4, 5, 6, 7, 8 DLLs, and then OK. Give Visual Basic just a moment to add those. And then we'll choose Show All Files and Expand References, and there they are. So then next we're going to go back to our project here and then add existing item, and we're going to navigate back to the Emgu install. So there we go, Emgu, Windows x86, bin, x86, and all files, and show all files rather, and then we're going to choose all the ones that start OpenCV and NDLL. There we go, and give Visual Basic just a moment to add those. And then of course we always want to highlight all these DLLs here, and then by copy to output directory, choose copy always, and let's go ahead and save it. And we can save it to our usual location here. Let's call it Surf, and create directory for solution is unchecked. It'll still create a directory for us. Let's go ahead and choose Save, and then we're going to expand our form. Alrighty, so our form's all set now. So let's go ahead and start writing our code here. We're going to have 12 functions in our program today. So let's go ahead and get our 12 functions set up, and then we'll come back and write each one individually. So of course we're going to start out with option strict at the top here. Always a good idea with Visual Basic. Then we're going to have our imports. Alrighty, so we're all set on our imports. Let's go ahead and put a comment in here for our member variable section. And then we're going to write our 12 functions, and the environment's going to start 10 of those 12 for us. So the first function, the environment's not going to start. That's going to be the constructor, so we'll go ahead and get a comment started for that. And now we're going to write the 10 functions, or rather start the 10 functions that the environment's going to start for us. So what we're going to do is we're going to return to our editor here and then click on the form. And then we're going to choose the resize event. And there we go. And then back to design view again. And now we can simply double click on the form to choose the check changed event for the radio button for the image file on the webcam. There's the image file, there's the webcam, and back to design view. And we can do the same for the button click event for the image scene button and the image define button. So there's those two. And now two more that we're going to choose individually are the text change event for each of the text boxes here. So we're going to scroll down on text box image scene to text changed. And there we go. And then the same thing for text image defined. And text change, there we go. And now the next three we can simply click on the form on the control. That's going to be the perform surf or get image to track click event. There we go. And also the checkboxes for draw key points and draw matching lines. That's going to be the check changed event. We can simply double click on the control on the form and that'll start that for us. Go ahead and save it. And now our last function we're going to start ourselves. This will be the function that's actually going to do the processing. So we're going to call that sub perform surf detection and update GUI. And so we can add it to our application's idle list of tasks. We have to put a sender as object and an arg as event args. And let's go ahead and neaten up our code a bit. Alrighty, so now everything's all set up for us and we're ready to start diving into our code. All the functions up until we get back down to perform surf detection and update GUI are going to be pretty straightforward Visual Basic form code and also pretty similar to the previous video. So I'm going to go ahead and fast forward through those, and then when we get down to perform surf detection and update GUI, we'll go ahead and slow it down and take a look at the computer vision part of the program line by line. Alrighty, well that was a lot of form processing code there, wasn't it? But we're finally to the perform surf detection and update GUI function. So the first thing we're going to do is we're going to take a look at the radio buttons for the image file and the webcam, and we're going to see if they're checked. So we'll do if RDO image file dot checked is true, and then we'll do else if RDO webcam dot checked is true. So here we're going to have these two blocks here within this conditional. So the idea is if the image file is checked, if we're working from still images, by the time this function is called, both images should be loaded and should definitely not be null. So we're going to go ahead and check for that first. If either is not there, then we're going to show the error message on the title bar text and then bail. If they are both there, then we're going to update the title bar text to indicate that we're processing the image at that time, and then we're going to call do events to allow that title bar text to update, and then we're going to start the stopwatch. Okay, so now we're ready to consider the case of using the webcam. So the first thing we're going to do is we're going to get the image seen from the webcam, and then we're going to make sure that that is not a null image. In either case, if we don't get it successfully or if it's null, we're going to return. Okay, so next we need to consider two different cases for the webcam being used. So the first time that the webcam is chosen, an image to track isn't going to be chosen yet. So we need to have a case where we check for the image defined, and if that's null, what we're going to do is we're simply going to show the image seen on the image box on the form and then return from the function. Because if the function went on from that point and we started performing manipulations on the image defined with it being null, the program would crash, of course. So then we'll have a conditional where if the image defined is there, in other words it's not nothing, then we're going to skip over the return statement and continue on with the rest of the function. Okay, so we finally know that both our images are good if we get to this point, and we're ready to perform our surf detection. Now in this next section of the program, this is pretty lengthy. There's a lot of objects for surf detection and a lot of functions for that. To keep this video down to at least a remotely reasonable length of time, it's already going to be pretty long, but to not make it really excessively long, I'll explain to some degree what these objects and functions are doing, but I can't explain it all. What I would suggest, if you're looking for additional information, some sources I would recommend are the Emgu website. Specifically, there's some forums on there which are excellent. The people are very helpful and they're very good about answering questions, as well as the OpenCV website. The internet generally, there's a lot out there on OpenCV and EmguCV, and then also specifically the paper by the inventors of the surf algorithm that I had mentioned at the beginning of the video. Those are definitely kind of your first go-to sources for further details on the surf algorithm. You can also download the OpenCV source, and if you compile it from sources in video 3, you can take a look at the source and see how the surf algorithm works internally. Unfortunately, I'm going to have to truncate my descriptions to a degree here to keep the length of the video down. But anyhow, I think proceeding, here's how I'm going to do it is, let's declare all the variables pertaining to the surf algorithm first, and then I'll try and comment those as best as possible. And then what we'll do is we'll use them all second. Now, of course, in .NET, it's not really necessary to do that. You can declare the variables as you go, but I think it'll be a little bit more readable to declare all the variables up front so you can see what we're going to work with, and then we'll run through the functions that use them. So that completes declaring all the objects that we're going to use for our surf detection. It's quite a few, as you can see. Of course, many of these are underlined green, and that's simply because we haven't used them yet in the cases of where we did not assign the variable, or object rather, to a default value. But that's okay, we're going to use them all later. So the first thing that we're going to do is, for purposes of displaying on the form, we've left the images as color. But to feed them into the surf functions, we're going to need to convert them to grayscale. So let's do that first. Okay, so now we're ready to make our first surf detection function calls. So what we're going to do is we're going to start with the scene image. We're going to call detect key points raw on the image scene, and that's going to return our vector of key points for the image scene. And then we're going to pass into the function compute descriptors raw both the image scene and also the vector of key points for the scene, and that's going to return our matrix scene descriptor for the image scene. So here's how that's going to look. Okay, so now we're going to do the same two function calls, detect key points raw and compute descriptors raw, only we're going to make those function calls now on the image that we're trying to find in the scene. Okay, so next we're going to instantiate the brute force matcher, and then we're going to add the matrix for the image that we're going to find. We're going to add the matrix of descriptors, I should say, for the image that we're going to find to the brute force matcher. Okay, so next we're going to instantiate the match indices matrix and the distance matrix. And the reason we waited until this point to do that is that the constructors for the match indices matrix and the distance matrix take as parameters to them the scene descriptors matrix, and then which we didn't have until the previous few function calls, and then also the k number of nearest neighbors. Okay, so now we're ready to call brute force matcher.knn match, and at least in the Emgu implementation, knn match is not overloaded, and of course it finds the k nearest match. And being that it's not overloaded, it takes 5 parameters. The last parameter is a mask, so we can simply not use that. We can pass in nothing for the mask. But for the first 4 parameters, what we're going to pass in is going to be the scene descriptors matrix, then the match indices matrix, then the distance matrix, and then the k number of nearest neighbors that we've declared to be 2 above. So next we're going to instantiate the mask matrix, and then we're going to set all values to be 255. Okay, so next we're ready to call the vote for uniqueness function, and this function is a member of the features 2D toolbox object. This is the first time so far in this function we're going to use the features 2D toolbox object, but we're going to use it a handful more times than the rest of the function. And what the vote for uniqueness function does is it filters the matched features. In other words, if a feature is a match is not unique, then it's rejected. And this takes 3 parameters: the distance matrix, the uniqueness threshold that we declared above, and also the mask matrix. Okay, so next we're going to use the CV invoke object. Specifically, we're going to use CV invoke.cv count non-zero, and what we're going to use count non-zero to do is count how many non-zero elements there are in the mask matrix, and we're going to store that in the variable int number of non-zero elements, and then we're going to check if that's at least 4, and if so, we're going to enter a conditional block. Okay, so next we're going to use the features 2D toolbox object again. This time we're going to call vote for size and orientation, and this function takes quite a few parameters. It takes the 2 find key points, the scene key points, the match indices matrix, the mask matrix, and the scale, increment, and rotation bins variables that we declared earlier. So here's how that's going to look. So now that we've returned the result of vote for size and orientation into in number of non-zero elements, we're going to check and make sure that that's greater than or equal to 4 again, and if so, we're going to call features.dToolbox.getHomography matrix from matched features, and the function getHomography matrix from matched features is going to return the homography matrix, which you'll see later on we're going to use to project the points of the image that we found onto the scene. Okay, so the next thing that we're going to do is we're going to make a copy of the image to find, and then we're going to draw a border around that. That way when it's presented in the image box on the form, it'll be clear which image is the image to find off to the side versus which is the scene image, having a border around the to find image. Now the reason that we want to make a copy is that we don't want to draw on the actual original image, because if we did and then we called the surf function again without loading a new image to find, then we wouldn't actually be looking for the image to find anymore. We'd be looking for the image to find with the artificial border that we just drew around it. So to avoid that concern, we'll make a copy first. So here's how that's going to look. Okay, so next we're going to get ready to assemble our result image, and what that's going to be is we're going to take the scene image and the image to find, and we're going to concatenate them together into the result image, and then later on we'll end up showing the result image on the form. Now we're going to need to do one of three different things here. We're going to have 3 different conditionals for depending on if the checkbox for draw key points is checked, and also depending on if the checkbox for draw matching lines is checked. So first let's set up our 3 conditionals, and then we'll write each of the 3 specific situations. Okay, so now we're ready to consider each of the 3 conditional cases depending on the checkbox state for the draw key points checkbox and the matching lines checkbox. So the first case we're going to take, where we're drawing both the key points and the matching lines, we can take advantage of a function in features 2D toolbox, and that function is draw matches. And what that function does is it's going to combine the scene image and the copy of the scene image with the border into a resulting image, and then it's also going to draw the key points and matching lines on the resulting image all in one step. So we're going to assign that result to image result, and that'll take care of all of it in one function call. So here's how that's going to look. Okay, so now we're ready to consider the case where we're going to be drawing the key points but not the matching lines, and this is going to be a little bit more involved. We're going to need 3 function calls here. First, what we're going to do is we're going to call features 2D toolbox dot draw key points, and we're going to pass in the image scene color as well as some other parameters, and we're going to assign the result of that to image result. So at that point, image result is going to be only the scene image but with the key points on it. Then we're going to call features 2D toolbox.draw key points again, and we're going to return the result of that. We're going to pass in the image defined, and we're going to return the result into the image defined, the temporary image with the border. So at that point, the temporary image with the border is also going to have the key points drawn on it. Then we're going to call the Emgu concatenate horizontal function to add the copy of the image with the border to find that now also has the key points onto the result image, which previously was actually just the scene image. So that's going to concatenate them all, and we're going to return that into image result. So here's how all that's going to look. Now we're ready to consider the last of the 3 cases where we're not drawing key points or the matching lines. This case is more simple than the previous ones. In this case, we're simply going to assign the color scene image to result, and then we're going to concatenate the copy of the image defined with the border onto result, returning that concatenation into result. Now you might note that we haven't drawn the red box around the image where we've found the image defined yet in the scene. In all three cases we're going to do that always, but we'll get to that a little bit later, as you'll see. Okay, so we're now to our last conditional block for the surf detection function. And what we're going to do in this conditional block is we're going to draw a border around where we found the image that we were looking for in the image scene. Actually, we're going to draw it on the result image, but it's going to be in the scene portion of the result image. And we're going to start that out with a conditional statement. We're going to check to make sure that homography matrix is not nothing. And the reason that we need to do that, if we look up here, homography matrix is only instantiated if we get past these two conditionals. So, and in this last conditional block, we're going to use the homography matrix's project points function to draw the image that we found onto the result image. So we're going to need to start out by making sure that homography matrix is not null, and then if so, then we can go about declaring our 2-point arrays and drawing the box around the image that we found. So here's how we're going to do that. Okay, so if we momentarily come back up to the top here and we take a look at these three variables, here's what we're going to work with in this conditional block at the end. Rect image defined, and the points F array, and then also the points array. So to start with, what we're going to do is we're going to assign the rect image defined to be equal in size to a rectangle surrounding the image defined. Not where it is in the scene yet, because we don't know that yet. The homography matrix project points functions is going to take care of that momentarily, but to have some numbers to start with as a default, we'll assign the rect image defined to be a rectangle of the size surrounding the image defined. Okay, so the next thing that we're going to do is we're going to instantiate the points F array. And what we're going to use to instantiate it is the same dimensions that we just assigned to the rectangle. Now, even though that doesn't at all correspond to where the found image is in the scene, that's okay, because what we're going to do momentarily is we're going to call the homography matrix's project points function, and that's going to modify the points F array so that it's going to end up being the location of the object that we found in the scene. But we'll get to that in a moment. So first, let's instantiate the points F array. Okay, so now that we've instantiated the points F array, what we're going to do is we're going to pass that into the homography matrix's project points function. And the project points function is going to modify, this is passed by reference here, the points F array to end up being the location of a box surrounding the image that we're looking for in the image scene. So here's how that's going to look. Okay, so now we finally have the answer we've been looking for all along. The array points F contains the 4 points in the scene surrounding the image that we're looking for. But there's one more step before we can actually go ahead and draw that rectangle around the image, the item that we're looking for rather. What we're going to do is we're going to declare a points array, an integer type points array. And the reason that we're going to do that is because we're going to pass that into the draw polyline function, and that takes an integer points array, not a floating point points array. So that's just one more step, and here's how that's going to look. Okay, so now we're finally ready to draw the border around the image that we found in the scene portion of the result image with the polyline function. And here's how that's going to look. Okay, so now there's just two things left. We have our good resulting image now, so we're going to assign the result image to the image box on the form so the user can see it, of course, and then also if the radio button for image file is checked, in other words if we're working with still images, we're going to stop the stopwatch that we started earlier, and then we're going to compute the processing time and display that on the title bar text of the form. So here's how that's going to look. Alrighty, so that completes our perform surf function and also our program. So let's go ahead and do a compile. And hey, how about that? One succeeded on the first go. So let's go ahead and fire it up and give it a test run. So to start with, let's use the example image and image define that ship with both OpenCV and Emgu CV. And there we go. It's all working great for us, and of course we can uncheck the matching lines and the key points, or we can leave them in if we like. And let's try the stop sign image again. And there we go, that's working great. Let's test the webcam out again, so turn the autofocus back on. And let's go with the same stamp book as before. And bear with me a moment here while I kind of zoom it in a little better. There we go. And we'll go ahead and turn the autofocus off when we're actually tracking it. Seems to work better that way. And there we go, it's tracking great. And we can go ahead and turn the matching lines off or key points off if we like to make the image a little bit less cluttered. And there we go, that's working real well for us. So we can draw these back, turn these back on if we like. And of course it's rotation invariant as we saw before, so we can rotate it around any which way we prefer. Now let's go back and look at a few more still images. Here's this nice image of the BMW Sauber F1 car, and there we have nice detect on the intel. And then also our Beverly Hills sign. And let's go ahead and finish with this nice railroad crossing sign detection. And let's make our window a little bigger so we can see it all, and there we go. Congratulations! You now know how to perform object detection and tracking via the speeded up robust features or SURF functions in Emgu CV. See everybody next time.